Okay, this morning we're going to talk about the section on harm. I used to start by saying that if you find this stuff interesting, you should be institutionalized. I don't do that anymore. I just show a picture of Bill Cordell. It has more impact. If you like it, this is what you look like. To be honest with you, this was a grueling task for me, and I really didn't find it all that interesting, but the thing that actually convinced me that it's the right path to take is because, above all, I am a dedicated lazy ass. And the nice thing about this is it's kind of statistics light. It sort of puts an article in your hand and says, now, this is the stuff you need to know in order to figure out whether this article is a good article or not. If you look at some of the stuff that's out there, there are some great controversies in medicine. And I'm the medical director at the Poison Center. I'm a toxicologist. And basically, we take care of people who are overdosed or have occupational or environmental exposures, that sort of stuff. There's a lot of stuff in tox that, well, for one, we're hardly treating patients based on science. I mean, I'll show you some of the things you choose. I will leave out what we use most, and that is witchcraft and guesswork. But the thing about this is that this is kind of a shortcut to looking at the medical literature, and it's a lot easier than the alternative. When you look at things you rely on to see patients, personal experience is one. Now, you guys are just getting started, so I would think most of you don't have a great deal of personal experience, but that will come in time. The other thing that you do is you can rely on the experience of colleagues. And as a matter of fact, that's known as a consult. You call up a friend and say, what do you think about this? And then they get paid money for seeing the patient, too. So there are those two things. Another thing is, and this is probably what you're going to depend on most right now, that's what you've been taught so far. And what are you 2 weeks into it? Okay, well, that one doesn't work too well either, does it? But it will. And then probably the most common thing that you'll rely upon for the next few years is going to be what you see in textbooks and review articles and things like that. I mean, the truth of the matter is there's a lot of hard science to look at out there, but you have to lay a framework for it, and that's what you're going to be doing. And then finally, and this is where EBM fits in, is their scientific medical literature. So what happens is just because you have a question about something doesn't mean that you're necessarily going to go to the library and pull every article on it. Eventually, you will be doing stuff like that. But right now, it's a little on the early side for it. So what I'm trying to say is, when I first started dealing with EBM, what I was hearing from people was, this is the do-all, end-all. This is how you will treat patients. That's not really true. It is one of the tools that you use, but it is not necessarily even the largest one. And when you think about it, this really applies mostly to epidemiologic studies. Now, when you look at medical literature, one of the things you want to do is look for literature that's not trying to influence you, but is just trying to tell stuff. Let me give you an example. How many people in this room feel that secondhand smoke is a decided human health hazard? Do we have any takers on that? A lot. How many people think it is not? Okay, we've got a few. And how many people don't know? And how many people don't give a crap? Okay, so in 2003 in the British Medical Journal, a vaunted journal, there was an article looking at 40 years of study regarding non-smokers living in a house with a smoker. And they looked for, does it cause heart disease? Does it cause lung cancer? Does it cause stroke? And you know what they found? They didn't find any statistically significant difference in the two. It was a 40-year study, 38, I think, actually, that involved something like 117,000 study patients and about 35,000 controls. And still, they couldn't show anything statistically significant. Now, the interesting thing about it is, boy, you would think a study like that would get them a lot of kudos. Nice job, guys. No, they were absolutely savaged in the medical community because they were saying something that people don't want to hear. Now, you can make up your minds as to who's right when we do the, holding up the hands. There are certainly studies out there that show that secondhand smoke is a health hazard. But as we look today, one of the things we're going to talk about is you have to look at the type of study that we're talking about. In other words, was that study a randomized controlled trial, or was that study a cohort study, or was it a case control study, in order to decide what validity you will assign to it. So one of the places that you look, or the place that you look, is in peer-reviewed journals. Give me a head nod. You guys know what I'm talking about when I say peer-reviewed? Okay. I'm seeing some heads nodding and some not, so I'll assume maybe not everybody does. So what happens is, let's say you do a study, you want to write it up. You send it off to the New England Journal of Medicine. They look at it. They're never satisfied with it on the first round. No journal is. They turn it around, and what they'll do is when you send it to them, they give it to a bunch of people who work in the field that you're talking about, where your study has been done. And those people will look at it, and they will criticize it. If there's one thing physicians are really good at, it's being critical of stuff. And so they will send it back, and then the journal will send it back to you and say, we want to see these changes, or you can't put this in. And then you make the changes, and it goes back. So peer review is just having people who are your peers, and sometimes they are, sometimes they're not, looking at that and critiquing it, so that it's not just one person's idea about what's going on out there. Randomized controlled trials are where you start off, you design the study, you decide what you're going to look for, and then you have a control group and you have a study group, and you do this prospectively. You sit down, figure things out before you start the study. They take a lot more work than other forms or other types of studies. They take a lot more time. But they do give you more reliable information. So that if you have the results of a randomized controlled trial, and you find that there is a 1.5 increase in risk of something, if it's an RCT and it's actually statistically significant, the confidence intervals are good, we'll talk about that, then you've got something. You can say, well, that looks like that looks like pretty good information, and that may influence your practice. But on the other hand, there are a lot of issues that you might want to try to study that you just can't do with an RCT. For example, we'll talk a little bit about studying benzene's effects and causing leukemia. Well, for one, acute myelogenous leukemia occurs at an instance about 1 out of every 100,000 people, okay? So it's not happening a lot. And if you're doing a prospective study trying to catch that 1 out of every 100,000, good Lord, how many people would you have to study with a randomized controlled trial? So that would be prohibitive in and of itself. But think of the time. There's a lag phase. I mean, it may be 10 years or 20 years before you actually start to show signs of your benzene exposure. So there again, now you've got to do a huge number of people for a long, long time. So there are other types of studies that actually start off with the people who have the disease and look at it that way, so that they can get a study group that has the disease and will give them meaningful results. But so in other words, RCTs aren't used very much for harm, okay? For looking for exposures or diseases that cause risk. And it's not because it's not a good type of study, it's because it takes so much time to do. Now for RCTs, you'll note this is a therapy study, and we're talking about harm. I realized this morning there's actually a very good example to give you of this, but it was too late for me to put it in, and that's the Vioxx trials. Vioxx trials didn't turn out, they didn't start out to look at harm. What they were doing is they were looking at how well that drug would work as therapy, okay? But what they discovered along the way was there was an increased incidence in heart attacks when compared to some of the other nonsteroidals. And it was particularly in patients who already were at risk. Okay, so you heard about that the trial and a huge award, right? Well, what they discovered was that there was, I don't know, I think it was like a 1.2, 1.3 times risk of having a heart attack while you're taking Vioxx. And particularly among the patient population that already had heart disease or had previous MIs, that sort of thing. And the thing that got them, so as you look at it, it looked like it was statistically significant. It looked like it was real. It looked like it was really pretty small. And it might have been something that they could have worked with, but the problem that they ran into was there were a lot of memos that went back and forth in Merck that kind of showed that what they were doing was they were trying to bury that information and present other things. I think that's why the jury awarded something like $250 million. I've been in medicine for a long time, and especially during my years in emergency medicine, I resuscitated a lot of people. And I got to tell you, as I stand here, not one single person that I resuscitated ever came back and gave me $250 million. I'm waiting, but I'm not holding my breath. So anyway, to go back to the RCT, this is an RCT about hyperbaric oxygen therapy for carbon monoxide, one of the big controversies in medicine. A lot of people, particularly the ones who have chambers, say that HBO is good. A lot of the people who don't have chambers say that it doesn't do anything. There have been about 5 RCTs now, and this is also to show you that just because you do an RCT doesn't mean they're going to wind up with a good answer. The first one was done back in the 80s by Raphael in France. They looked at something like, I think it was 600 patients. May have actually been more than that. May have been twice that. And they divided them up. They didn't do a very good job of randomizing because what they did was they did every other one. Okay, you go to HBO. You don't. Well, that's not really random, okay? But that aside, they were the first ones who actually had the courage to say, okay, we're not just going to jump in and do HBO on all these patients. And you find in research that is a pretty important problem, and that is when you start off with a therapy, for example, that you're trying to research, nobody wants it. They all want to be in the control group, and if it starts looking like it works, then everybody wants to be in the study group and screw the control group. So what happened here was the HBO group, it took some courage to go before an IRB and say, this thing that we consider standard of care, we've decided we want to withhold from some patients. And lo and behold, after they did that, it showed that there was no benefit to HBO, okay, which made a lot of people angry, which got a lot of letters to the editor, which talked about what scumbags these people were because they were fighting against the vaunted HBO therapy. So then there were a couple more RCTs that came out. One that was smaller showed there was a benefit. One that was larger showed there wasn't, maybe a little bit of harm to HBO. And then most recently is this one by Weaver that shows that there is a mild benefit. So let's go back to why we're talking about evidence-based medicine. You now got something like 5 randomized controlled trials, all of which are, you have them showing things on both sides of the track. You need to be able to go back and try to figure out what are the valid studies so you can tell which are the valid conclusions. And the more I look at this stuff, because we dive patients, but I can tell you the science just is not there. I mean, I think it's one of those things where there probably isn't a difference, and that's why studies keep falling so close to the middle, why you get a few that say, nah, it doesn't really work, and you get a few that say, yeah, it kind of does. Okay. But this is one of the big controversies in medicine. Another big controversy is how much lead is too much lead. And so you see a lot of longitudinal studies that are epidemiologic in nature, and you need to know what to make of them as you're reading them. Now, one of the ways you can get around the problems with having an RCT, that is that they are so long and so labor-intensive, one of the things you can do is you can pick out a group of people who have an exposure, let's say, to, you can make it a virus, you can make it a toxin, but an exposure of some sort. And you look at another group that is almost exactly like the first group but has not had that exposure. And then you figure out which one you look for, how often the disease pops up among those cohorts, okay? So you start, let's say we're going to talk benzene. You start with people who are exposed to benzene. And your control population, a lot of this has been done, say, in petroleum plants. So you got people who are working out there around the pipes, and they are being exposed to benzene. And then you've got people who are working in the office up front, and they are not exposed to benzene in that setting. And so what you do is you follow those two groups for several years and find out who's getting leukemias and what kind of leukemias they are. And those studies have been done and actually are ongoing. And what you're trying to do is determine what the risk of leukemia is among the exposed population. So you want your two populations to be as close as possible. The nice thing about this is that nobody in these studies has to have treatment withheld. Okay, you're just picking out exposed people and non-exposed people, and if they get the disease, you treat them. And these can be either prospective or retrospective. The investigator doesn't really control the exposure, and it's less intensive or expensive and less time-consuming than an RCT. But the downside is it does not give you data that are as reliable as an RCT does. Okay, so that when you get a result, you want to see a bigger difference. You want to see a higher risk. You follow what I'm saying? If an RCT says you got a 1.5 times chance of getting this, then you can tend to put a little bit of stock on that because it's a better type of trial. But if you get a cohort study that says that, generally people will say there are enough possibilities for mistakes here that in a cohort we want to see a bigger difference in risk. Okay, not randomized. You can have confounders. And they generally will require a large sample study and long follow-up. There have been a lot of these looking at lead poisoning in children, and they'll follow for, they've got studies been going on for 30 years. And I mentioned the cohort study that was done on secondhand smoke, which was a 38-year study. It's kind of funny. It started off being funded by the American Cancer Society, and after about 18 years, when they weren't showing any difference, the American Cancer Society said, we don't really see a point in funding this anymore. But the American Tobacco Company said, but we do. And they actually took over funding and completed it. So anyway, you can establish timing, directionality of events, and you can establish prevalence. Now, prevalence is the rate of harm in a population at a single point, okay? So where you would say, like for benzene, I mentioned a case in 100,000 people, that would be the prevalence. And incidence looks at the rate that occurs over a given number of time, or amount of time. Okay, so here's an example of a benzene study. I'll come back to this in a little bit because when we talk about confidence intervals, I want you to see this. Now, cohort study basically looks at who was exposed versus who was not exposed, and then they try to figure out who's been harmed. Okay, so your starting population is exposed, but they don't have the disease necessarily. Okay, when we talk about case control, what you're going to do is you're going to start with people who have the disease and look back and see who got exposed. So essentially what you have to do in this is you're looking for people who are exposed to benzene. Not everybody gets leukemia that's been exposed to benzene. Some people do. And you use these god-awful boxes to figure out for a cohort study to be relative risk. What outcomes were measured, and were they measured equally? Was there a complete follow-up so that your numbers are okay? And then I'll leave for you if anybody wants to calculate relative risk, which sometimes is probably worth doing, but to be honest with you, probably almost never gets done. I mean, we show you this, but and there may be a few people out there that will look at it and make sure that the people who did it are showing you accurate numbers. But it is figured by using the box system. Let me warn you about something, though. While the boxes aren't particularly interesting, they are found fascinating by people who make board exams. So before you take any test in medicine, you want to understand the boxes. And it's because it crosses all lines of medicine. It's not just in internal medicine or it's not in plastic surgery. I mean, it's across the board. Everybody likes to put these on a test. Okay, so what they found was, in the study that I'm showing you, is that the relative risk was 3.1, okay? So if you were exposed to benzene, 3.1 times the non-exposed group, 95% confidence intervals. And essentially, what you're saying here with 95% confidence intervals is if you did this test 100 times, 95% of the time, it would fall out in the 1.2 to 10.7 range. And we'll come back to that a little bit more because it says more than just that. So case control studies. Well, if you have a really rare disease, you probably would look to do a case control study because what you do here is you pick out people who have the disease and then compare them to people who don't and look at what they might have been exposed to. This was a case control study that was in the New England Journal of Medicine. Now, the New England Journal of Medicine, again, is a vaunted publication. But being vaunted does not prohibit you from publishing crap every once in a while. So it's still worth looking at to decide what you've got. The reason why this one was important was it was published, as you can see, in 2000 shortly. In fact, it actually it came out in press a little bit after phenylpropanolamine was taken off the market, and the FDA took it off the market because of this study. And then when you look at the study, you say, what were they thinking? So essentially what you do in this case, they started with an outcome, which was hemorrhagic stroke. And that was the study group, people who had had hemorrhagic stroke. And then you find control groups that are as close to these people as you can make them, but don't have hemorrhagic stroke. And then you look back to see if there was an exposure that increased their risk. And this determines an odds ratio. I'll mention that. You'll notice that for case controls, it's an odds ratio, and it's relative risk for cohort studies. Why is that? It's because the way you're setting this up, with a cohort study, you're starting with an exposed population. With a case control study, you're starting with a population that has a disease. So your math is different, and therefore you have to call what you get a little bit differently. These are both looking at what risk is, but it's a different term. Does that make sense? Okay. Okay, so these are quick, easy, well, relatively quick, relatively easy, and relatively inexpensive to do. But you really need to find well-matched controls. You've got people that have the disease and people who don't, but you want them to be alike in other ways. It's very good for rare disorders, and the problem is that it relies on people's recall, and that can be quite variable as to what, because you're asking them to remember what their exposure was. And a lot of times they've been exposed and they don't know it. A lot of times they've been exposed and they don't remember it. And then the people who have the disease are more likely to remember that they were exposed to something than people who weren't. So there are some flaws with this. Essentially what you're doing this time is you're starting with the people who have suffered harm, and then you're looking back to see what exposure they've had. Okay, again, the 2x2 tables. Again, you want to make sure that outcomes and exposures were measured equally, and was there complete follow-up. This turns out to be a big flaw in most studies because, as you might guess, if you have a study group, patients just aren't as interested in finding the answers. I mean, they got the disease. It's 100%. So following up with people becomes a very difficult thing, and a lot of times studies have major flaws simply because their follow-up was so lousy. Okay, odds ratios, there's the formula. In this study that I was telling you about, the authors say that the results suggested phenylpropanolamine in appetite suppressants and possibly in cough and cold remedies is an independent risk factor for hemorrhagic stroke in women. I'll show you in just a little bit how that's a real overstatement of what they got. Okay. Now case reports. They're less reliable. I worked with someone who once said that he felt that case studies were such poor science that they shouldn't even be published. But the truth of the matter is there's a lot of stuff that we do that there are no RCTs for, there are no cohort studies. And so all you've got is you got a sick patient and you say, gee, I wonder what's going to happen with this, and you go look for case reports. We had somebody who was admitted over at University Hospital, arsine gas exposures. Well, there are lots of cases of arsine gas exposure. It's an arsenic gas. Causes profound hemolysis, causes renal failure, can cause death in people. And so we went back and looked at how people have been treated. There really aren't RCTs out there because, how are you going to sign people up? Now, which of you want to be arsine exposed? You'll get more money. So a lot of times what you're left with are case reports. And a case series, of course, is better than the case report. And there are some things that can't be staged. I show you this. I looked this up in Ovid the other day. It's not even in there. But a few years ago, we had somebody that was exposed to dipropylene glycol monomethyl ether. And this is a solvent that's used in industry. It's actually considered to be safer than some of the glycol ethers that are used or have been used in the past. This woman was working one day, picked up a bottle and drank half of it and had a cardiac arrest. So they transferred her into us. One of the questions was, do we need to dialyze this lady? And so we started trying to figure that out, and we started going through our computer databases. And we have pretty significant computer databases, and we started pulling literature. And you know what? There wasn't anything written about this stuff. And you'd be surprised how often that happens. There just hadn't been any cases of it. And so we wrote it up and presented it in abstract form. The lady did okay. We actually just treated her supportively and didn't have to dialyze her. But the funny thing is that after doing that, it's still not in the literature. If you tried to look it up today, you couldn't find it. But for things like this, I mean, you're just not going to get very many folks who want to fund trials for something as unusual as that. Phocomelia in Germany is an example of how case control studies, or rather case series, can be very helpful. It turns out that in the up until about 1960, phocomelia is a debilitating birth defect. And if you look here, you can see that, remarkably, a lot of these kids really learn to cope with this very well. But if you look at the numbers, you'll start to see why cases are rather important. Up until 1959, this was really a rare disease. Phoco means seal. Phocomelia, rather, means seal limb. Actually, melia may be seal. At any rate, it means seal limb. And so what happened was, in 1960, there were 17 cases that occurred, and it was more in Europe where this was being seen, because in the United States it wasn't being marketed yet, although there were some cases that occurred here. But look at what happens in 61. There's 136. This used to be a rare disease, and between 60 and 63, there's something like 733 cases. Now, the importance of case reports is that they serve as surveillance for what's going on out there. If you look at what the federal government does, they have MedWatch, okay, for the FDA. And what they report in MedWatch is adverse incidents that occur. And you can basically call in and say, you know, I took a pill of this and then my stomach hurt. And they'll write it down, okay? I used this nasal spray and somebody rear-ended the back of my car, okay? May lead to traffic accidents. So there's really not any science there. They're just kind of recording the number of incidents that occur, so that at some point, if they see that, ephedra is what always comes to mind, where they start seeing there are a lot of cardiac events that are associated with the use of ephedra, then they start casting a more worried eye on those things, and people will start to do studies if they can. But if you look at something like phocomelia, even studying this turned out to be extremely difficult. They looked at it and said, what in the world is causing this? And it turned out that an antiemetic that was being used, which was thalidomide, was eventually found to be the thing that was causing it. The interesting thing is, if you want to study it, you'd say, okay, let's give it to animals and see. It turns out that about the only thing that you could give it to that would really cause problems was you could give it to rabbits. But rats, dogs, other animals just weren't as nearly as susceptible as humans and rabbits are. So there are a lot of things that are just extremely difficult to study, even if you go to animal studies. Okay, then there's the hierarchy. Some people argue this is basically meta-analysis. Randomized controlled trials are thought to be pretty much at the top. Cohort studies, then case controlled, then case series, and then there's physiologic rationale, which means that I know this makes you stop breathing, therefore I'm not going to give it to you. Okay, and there aren't many statistics associated with that one. Meta-analysis is basically taking a number of studies and folding them together and trying to find commonality in them. So you select search criteria and you put together, the nice thing about them is they put together a large body of data. One of the problems is there are multiple authors, so if everything meshes, then yeah, that's good because you got multiple authors. But a lot of times what happens is the multiple authors just kind of muddy the waters. And so often it's very difficult to extract data from these. But if you can come up with some meaningful stuff, they can be very helpful. And the physiologic rationale we've sort of addressed. So let's look a little bit at the numbers. First thing is, when you do those types of studies, what's considered significant risk? Remember that when we're talking cohort or we're talking case control study, that we're looking at a difference in terminology here. But if you have an RCT, for example, if you see something that increases your risk above 1, that's fairly reliable, provided everything looks good in the RCT. Cohort studies, you like to see a jump of more like 3, okay? I was mentioning in the cohort studies the secondhand smoke study. There are a lot of secondhand smoke studies out there that will show that there is an increase in risk of various, lung disease, heart disease, and that sort of stuff. But they're cohort studies, and so you got to look at them and say, yeah, but is the risk 1.2 or is it 4.5? Okay, that's one of the things you look at, because it's a cohort study. You want to see a little bit bigger risk than you would if these were RCTs. And if the case control study is even a greater risk, before you started to say, this may change the way I do things. Okay, if you think about confidence intervals for just a minute, basically what you're doing is you're doing a mathematical calculation to determine if your study could be due just to chance. Okay? Now, if I stood here and flipped a coin 10 times, how many times would I risk coming up with heads? Okay, well, you'd think it'd be about 5, but most of the time when you do that, it's going to be 6 or 4 or something like that. If you do it 100 times or 1,000 times, if you do it 1,000 times, you're still probably not going to break 500 and 500, right? But does that mean that it's not by chance? No, it doesn't. And so what you're doing here is you're trying to determine if you looked at, for example, that coin toss, if you did the study and it was 1,000 times, what you would find if you did that study multiple times, you'd probably have a range of, 475 for heads one time and 510 for heads another time. And so eventually you would wind up with a range that would probably be a little bit above and a little bit below breaking even, which would be considered 1. Okay, so your chance would be 1 time. Or so in some cases it might be 1.3 times. In some cases it might be 0.8. So that's what confidence intervals do, is they're just giving you an idea of how reliable that those results, that range that you're looking at, might be. And we talk about 90% or 95% confidence intervals, meaning that if we did that study 100 times, 90 or 95 times, it would show results in the range that we're looking at. Okay, so if you've got a positive number, you've shown a positive association. If we're looking at, and let's go back to the benzene example. If we're looking at folks have been exposed to benzene and they've got a 3.1 increase in risk, okay. But if we said, well, they've got a 0.8 increase in risk, that actually means benzene is good for you, okay? So that's why it's important. And when things start crossing 1, then you can't really, it's a real temptation to say that you've shown a difference. And in fact, here's an example. I'm going back to the cohort study that was done in workers in China, and they had, almost 75,000 exposed workers. And they said, acute myelogenous leukemia was significantly elevated. The relative risk was 3.1. And the confidence intervals, 95% confidence intervals, where are they here? 1.2 to 10.7. Okay. Well, what that shows you is that, yes, they are up. And, in fact, this was I believe it's a cohort study on that. And essentially, you've got a jump in risk that's probably going to be significant for AML. But they looked at other kinds of leukemia. And what's confusing to people, I was asked to look at a case a few years back where somebody had developed CML and worked in the petroleum industry and had been exposed to benzene. Well, when you look at some of the textbooks, they say that benzene causes leukemia. Yes, indeed it does. But does it cause CML? And when you look, and this was one of the articles I was looking at, The authors say they showed a non-significant excesses were noted for chronic myelogenous leukemia, CML, and they've got a relative risk of 2.6, but their confidence intervals are 0.7 to 16.9. So what do you make of that? Well, what you make of that is they should have just left this out because, I mean, they're saying, yeah, there was an increase, but it really didn't mean anything. Okay, if it didn't mean anything, then why waste paper printing it up? Well, the reason why you do that is because you want your study to look good enough that people will actually publish it. Okay, there's a publishing bias here. And so if you do a study and say, we did this study, spent a lot of money, really didn't prove anything, then a lot of times it doesn't get published. So what authors will sometimes do is they'll mention the non-significant excesses that they saw. And the other thing when you look at this is you see a pretty big range from 0.7 to 16.9. You'd like for that to be, down in the range of a span of about 6 or less. The tighter it gets, the better. When you see a big span like this, it tells you there probably weren't enough people in the study to really give you a good determination of the risk for that. Okay. This is a phenylpropanolamine study. This was a case control study, and I wanted to show you this. This is what got phenylpropanolamine off the market. It was really rather irritating because when something like that happens, people in the news media start looking for somebody to talk about it, and so they ran out trying to get folks to make comments about what do you think about taking phenylpropanolamine off the market, and about all we could say was we've not seen the literature. And so the thing that was really rather aggravating was the FDA did this in such a way that they could make the decision and get it into the press, but they didn't have to really show you upon what literature it was based, whether or not their study was any good, before it was too late to make any comment on it. And when you look, what you see here is women taking appetite suppressants as opposed to products that were for cough and cold appeared to have an increase in risk. And yes, it looks statistically significant, but boy, look at the jump, 1.5 to 182. You think they needed some more people in that study? Yeah, they really did. Now, that's a pretty big jump in risk, but also notice up here, when you're talking about cough and cold remedies, 1.54, but the interval actually includes 1, so that could be just chance. And yet, the authors concluded that it was definitely, women who took appetite suppressants with phenylpropanolamine definitely had an increased risk and probably had an increased risk due to cough-cold remedies, when in point of fact, that's not what they actually proved. If you look at men, confidence intervals for men all included 1. So hemorrhagic stroke risk in men appeared to be, the same as random chance. And so the other interesting thing that they did, and this is why you look at studies, is because now they've taken, I don't have any stock in phenylpropanolamine. And in fact, I think there are some problems with it. I mean, over the years, I've treated people who had some bad events that I thought probably were associated, but my N equals about, 4 or 5 and probably wouldn't get published in the New England Journal. But having said that, when you look at this study, the other thing was their study group all had a higher rate of cigarette smoking, history of hypertension, family history of stroke, alcohol use, cocaine use. Their study group had higher rate of this than their control group. So even without phenylpropanolamine, you probably would have seen this kind of stuff. So, now a decision's been made to take that off the market, and it was based on stuff that looks really suspicious. Okay, so how do you apply the results to patients and yourself? One of the things you do is you say, if this were my family, would I recommend that they stop this kind of exposure? Do I see significant harm? That for me is the gold standard. You run into stuff over the years where you've got data that are conflicting. In fact, I'll tell you where I use it. We get people in who say, well, I was breathing some fumes and I've got a carboxyhemoglobin level. Normal should be about less than 5%. And the patient's got a carboxyhemoglobin level of, say, 30 and they got a headache and they're a little nauseated. And I say, gee, should I put these people in an HBO chamber? And the question I ask is, if this were my wife, and I love my wife, by the way, I guess that. If this were my wife, would I put her in an HBO chamber? And actually, the way I usually answer that question is no, I wouldn't. I don't see a huge risk in it, but I don't see much of a benefit for that particular type of patient. What are the consequences of continuing the exposure? What are the consequences of stopping the exposure? An example of that would be, we see people all the time elderly patients who are on digitalis, and they come in because their dig level's high, and they're going into a little bit of renal failure. And you say, well, yeah, you'd like to get that down, but you also have to think, what if I give them digibine and I reverse all their dig? I may just discover the malady that got them put on dig in the first place, okay? So a lot of times giving antidotes and fixing things, giving antibiotics usually, but any kind of treatment is going to have potential for causing harm in and of itself. So you have to weigh that. Okay. Now, in terms of important points and things that you might want to know, you guys get tested, don't you? Okay. It's been about a year since I wrote the test questions. So this is just a guess. But if I were you, I would understand the differences between randomized controlled trials, cohort, case control studies, and a case series. I would know. I mean, you don't have to be highly technical about it. You want to know, like which one gives you the most reliable data, okay? Which ones require the most work? Which ones can be used for very uncommon illnesses or diseases. And then you want to know the studies that use what's the difference between relative risk and odds ratio. We've kind of talked about that. You're actually starting from a little different point in the groups that you're looking at. So even though you're looking at risk, it's not exactly the same. You need to know those calculations that I showed you, because I wouldn't be at all surprised. And of course, I can't remember very well if you're not given something where you have to use one of those god-awful boxes. What I can tell you is if I did that, and that was a year ago, that was the last time I did any box calculations, just to give you an idea of how. And then you need to know what confidence intervals are. You need to know that if you look at a confidence interval and it spans 1, that you may be looking at something that could have occurred simply by chance, and that you really haven't shown, you haven't demonstrated anything. I think the public gets the idea when we say something is not statistically significant, that we mean that as scientists, yeah, there's an increase in risk, but it's not our butt that's sick, so we don't really care because it's a small enough risk. Well, that's not the significance that we're talking about. It's that a lot of times people make big assertions about statistics that clearly show that they may be talking about random chance. Okay, so which is kind of redundant. So those are confidence intervals. Understand those things, and I think you'll probably do just fine. Okay?